Alright, in this video we're going to go ahead and take a look here at what should be labeled as example number 3. But for some reason I have this as example 6, which makes no sense. So we're going to go ahead and take a look at what we have here. This is a very, very strange sort of a function here to try to work with, in a similar way to what we did in the previous two examples. You might recall that in the previous two videos we took a look at two different functions and tried to find power series that modeled them. And that was easy to do because we were always able to take that function and kind of re-express it as the sum of a geometric series. But down here, I might really struggle to kind of get this thing here into the form of an a over a 1 minus r, right? Because like that seems maybe kind of difficult to do. I can maybe have an a up top, but I don't really have a 1 minus an r on bottom. And while I could possibly multiply a lot of things out here to maybe get a messy r, it'll actually be surprisingly simpler to attempt to do the following. So take a look at what I'm going to see here. I'll go ahead and write this. I'll say that using partial fractions, we can re-express g of x as g of x, again, which is equal to this x minus 1 over, 1 over x minus 1 times x minus 3. And I think that it's possible to rewrite this as a 1/2 over, oops, sorry, that is an incorrect denominator. It should be a 1/2, a negative 1/2 over a x minus 1, and then a 1/2 over an x minus a 3. Now I'm not going to go through the full work there to do the partial fractions, but I'll leave it to you to double check that that is actually correct. The nice thing is that once I do this, you might notice something. What do you see about the shape of each individual fraction? Well, you might notice that they both seem to resemble the sum of a geometric series. So I'm going to go ahead and do a little bit of work to get them fully there. On the bottom here, I'm going to have to go ahead and maybe reverse the order of the subtraction, which, of course, I can't just reverse the order of subtraction and get something equivalent. But if I multiply top and bottom by a negative 1, you'll see that the 1 on the bottom becomes positive, the x on the bottom becomes negative, and I get my a over 1 minus r shape. That's perfect. If I do the exact same thing on the other fraction, you'll notice that I just get 3 minus x, and so I don't really have this 1 minus r on the bottom. But we could easily fix that by, let me erase that really quick and rewrite. But we can easily go ahead and fix that by taking that second fraction and just dividing everything on top and bottom by a 3. Okay. So now I can see that each of these kind of resembles a geometric series. In fact, I'll even write that here. I'll say each fraction represents the sum of a geometric series. Okay? And I can be more specific. Okay? So I can say g of x, which again is this 1 over x minus 1 times the x minus 3, which again I can rewrite as each of these two separate fractions now. If I was to turn these into each a geometric series, the first one would look like a 1/2 times an x to the power of n, and the second one would look like a 1/6 with a x over 3 to the power of n. These would be the two different geometric series. And since actually both of these geometric series will converge for certain values of x, we even know that we could try to go ahead and combine these as one single one single series. So I can have a 1/2 x to the n minus a 1/6 x over 3 to the n. So I can get something like this as one giant series. Now, of course, I might want to know exactly when this is going to take place. So I might have to actually specify here that we need to determine where do these things converge. So I'll note down here that the first series converges when the absolute value of x is less than 1, since that's what was my value of r at that point. That's on the interval -1 to +1. And I can say that the second series converges when the absolute value of x minus 3 is less than 1. That, of course, gets me that x minus 3 should be in between -1 and +1, which ultimately produces that x should be between 3 and -3. Now, of course, if I need both of these things to be converging at the same time, I can then go ahead and kind of combine these and say that both series, in fact, let me go ahead, I don't like writing it over here. That doesn't seem to fit very well. I'll just write it on a new line. So both series converge. And I could think here, for what values of x do both series actually converge? What are values of x that can make the first series converge and make the second series converge? Take a moment and try to think about that. What are values that could make both of those intervals be satisfied? Well, if you're thinking here, it's actually just got to be the smaller one, right? Because if I want a value that's inside of the range -1 to 1, and I also want values inside the range -3 to 3, the only values that meet both descriptions simultaneously are the ones that are on, well, I guess this smaller interval. So then ultimately, I can make the claim that g of x is going to be equal to the sum of these two series with the interval of convergence -1 to 1. So again, this is a really, really cool way to try to go ahead and see that I can take a function like this g of x over here, and if I was to go ahead and write out these two series and subtract them, or this combined series, these should produce the exact same graph, but again, only on the interval from -1 to 1. We'll go ahead and actually summarize some of the results of what we've seen in these examples and some of the stuff that we'll see in the examples to come in the next video.